Good morning, people. I'm yet to see any comments and good morning wishes. I don't know what is the reason for that. Yeah, I can now see that 7 of you all have now joined. And yeah, Saloni, good morning. Ajay says good morning. Dheeraj, good morning. Sachin, good morning. Ria, good morning. Pratik, good morning. Brahmai, good morning. Sushil, good morning. Malvika, good morning. Saraswati, good morning. Saraswati, is it? Interesting spelling. Well, let us start with a few things. If you have checked, Sukhdev, good morning. If you have checked the thumbnail, I don't know how many of you all do it. Normally, I put up an interesting picture of in geography as far as the thumbnails are concerned. And today, I would say that I have tried to relate it to the content that we are going to do today. We are going to do the interior of the earth. And with regards that, the Kruti, good morning. With regards the interior of the earth, the photograph is basically a photograph of a mud volcano. This is in Indonesia. I don't know if other places have it in the world, but it's very interesting that a lot of mud volcanoes, as they're called, are in and around Indonesia. And if you see that Indonesia is very susceptible to volcanic eruptions, not all of it, but certain islands in Indonesia. So that is something that Nisha, good morning. That is something that would interest us. Okay, before we go to what we are going to start with today and what we have in plans for today, that's the interior of the Earth. Just a revision of a few things. The geological timescale that we have been doing for the last couple of so to say lectures, we know that the age of the earth is 4.6 billion years, and the fact that these 4.6 billion years are very long period. Okay, because as far as larger forms of life are concerned, they are seen to be there for the last 600 million years. So nearly 90% of the history of the earth, geological history of the earth, is not known to us. But we know quite a bit as far as the latter 600 million years as such, and we divided into various eras, periods, etc., etc. You'll see that we divide the periods, the era before the pre-Cambrian period as to before the Cambrian period to pre-Cambrian era. That's that making 90,000. 90%, sorry. That 90% is on a very broad scale divided into three parts. Let us say the first 500 million to 1 billion years of the history of the earth, wherein the surface was very molten and you had rivers of molten lava instead of rivers, water. Then you have the solidification, and it's during this solidification that the first of the cratons, as they are called, cratons, cratons came up. These are also called as the shields, and we said yesterday that peninsular India is one of those shields, and it is around these shields that the rest of the so to say the rest of the land material, or the crust material, we should be calling it more scientifically, has developed. And you'll see that every continent, as a matter of fact, has a central part called as the shield. You go to the Americas, you have the Canadian shield in North America, then you have the Brazilian shield in South America. As far as the South American continent, the Brazilian shield is concerned, those of who are from the SSC board, I suppose, had the say the regional geography of Brazil and India. I don't know whether it was there for you or not, but presently 10th standard has a comparative study of India and Brazil. So the Brazilian Shield. You come to Africa, the African Shield, and you go to Europe, you have the Siberian Shield, and of course the Australian Shield. So it's the craton or shield, you may call it, and then the development of the say land around it. Now, an obvious question would be that is land increasing even today? Well, wherever we have active volcanoes, yes, the crust is into a process of formation even today, as such. But now, when I say that land grew around the shields, it is not a matter of fact of a few thousand years or even a few 100 million years. It is for hundreds and hundreds and hundreds of millions of years that gradually these shields kept on gathering material around it, and possibly they have increased to our present size as such. Remember that at that point of time also, we have to remember that we did not have water on Earth as such. Now, there is a huge debate between scientists as far as occurrence of water on this particular planet is concerned. In fact, if you go in a chronological order, you'll see that the formation of the Earth is believed to be have formed of a lot of gaseous mass which solidified, and then you had countless number of meteors and comets which kept on falling into the surface. Now, why don't they fall today? Is basically because you have an atmosphere, and we are going to do how possibly next chapter, where in how the atmosphere prevents us from a lot of things, say cosmic waves and collision of smaller meteors and comets. Of course, larger ones do collapse, and in fact, if you remember when we were speaking about the extinction of dinosaurs, one of the reasons why which scientists predict or rather project there has been the for the extinction of dinosaurs is the fact that there was this huge meteor which collapsed somewhere near. This was as large as the size of say the whole of Mount Everest being thrown onto the surface of the Earth, and this collapsed somewhere at the Yucatan Peninsula. The Yucatan Peninsula, you'll see, is somewhere towards the northern side of South America. And this was not known for a significant period of time. This was understood only after we went into satellite technology, and when satellites started sending us satellite images, that something queer was being seen. Okay, because this crater was beneath the oceans. Okay, so identifying that crater took an advanced technology, I would say. So that is it, and it's all these meteors, etc., kept on collapsing, and the surface of the Earth was bubbling with volcanoes every here and there, and this went on for 500,000,000 to 1 billion years. You'll see that around this particular period, you had two types of lavas, okay, or crustal formations. We are going to speak about that when we speak about the crust also. You'll see that the crust that forms beneath the waters, or oceanic crust as it is called, it is formed out of basalt, and the land crust which is formed out of granite. Now remember, granite and basalt both are igneous rocks, but basalt is significantly dense and heavy and dark in color, and granite on the other hand is light and it's granular, and of course it is lighter in color also. So that's the basic difference. You'll see that you'll find more of land on granite on land surfaces, and as far as ocean bottoms are concerned, you have a lot of basalt. Now you'll see that these lavas which erupt at the base of these oceans, as they are called, these are called as pillow lavas, and the pressure of the water makes it dense and transfers it into basalt as such. Okay, coming back to the fact that as far as this water on this planet is concerned, some scientists believe that water on this planet is extraterrestrial. Okay, obviously not all of this, but a significant period. Now, what is the source? You don't see water in space, so how does it come? They believe that as far as meteors, etc., comets, etc., are concerned, they have some percentage of water in them, and when they collapse, and it was billions and billions of meteors which kept on colliding in the initial period, so all that water kept on accumulating on the surface, and gradually it grew to that particular number, and then say around 4 billion years ago. So it's 4 billion years ago would mean what? Towards the end of the first 700, 800 million years of the existence of the earth, say the surface was solidifying. So when it started solidifying, you had a lot of gases which came up, and because it was volcanic, a lot of sulfurous gases kept on coming up. And besides this, you had a lot of carbon dioxide also, and this carbon dioxide formed a lot of oil and water vapor, and of course all of this condensed to form clouds. And it is believed that it rained for not days and not months and not years, but for not even hundreds of years. It will rain for millions of years. Obviously, you'll see that the amount of water that you would be requiring to come down to fill all these oceans around us, it is but natural that it should have rained for millions of years to fill up all these depressions that we have around us. And now presently we call them as different oceans by these names: Indian Ocean and the Atlantic, and of course the largest one is the Pacific Ocean as such. Okay, so and initially you'll see that these oceanic waters were grayish in color because they had a lot of iron in them. It again took a few 100,000 million years for this iron to get oxidized. And when this oxidation took place, you'll see that the iron was removed from the oceanic waters, and the pale colors of the water started going, say more colorless and crystalline, as we should say. Okay, it is believed that it is during for a considerable period the carbon dioxide in the air was significantly high, and because it was significantly high, the surface temperatures then were 200 degrees Fahrenheit. Now we will have to convert this into Celsius. Remember, 200 degrees Fahrenheit is going to be higher, but when you convert it into degrees Celsius, it would be lower as such. So the I'm telling you this basically because you'll see that we are putting things together. Okay, if you have seen your syllabus, we were supposed to be speaking about Earth systems. Now we can't speak about present Earth systems, or rather we have spoken, but we can't go into the details of these Earth systems only until and unless we know the origin of this. So you'll see that the first of it was land, okay, which presently is the smallest, the solid part of it. Uh, Again, there is a debate whether atmosphere followed or um, water followed. Okay, but for water, we know that it rained for a few 100 million years for all this to happen. And you'll see that as far as the interior of the Earth is concerned, we are going to come to that. A certain arrangement of layers in the interior of the Earth led to the formation of what is called as the gravitational field of the Earth. And you'll see that the gravitational field of the Earth then started trapping various gases. You'll see that the heavier of the gases came down more nearer to the surface, and the lighter of the gases escaped further. And from an initial atmosphere of more of hydrogen and helium, presently we have come to the more heavier of the gases, that's nitrogen and oxygen, forming a major part. And you'll see that they further play a major role as far as other systems are concerned. So you'll see that it's so very in a perfect balance. You'll see that man has been researching, and we have the most modern forms of telescopes and etc. In spite of that, you'll see that we have not been able to locate any other civilization or any other type of life. Leave aside human beings, we have not been able to hear about any type of life in other. Yes, we have traces, etc. But again, you don't have proofs about that. So the fact that we have life on this planet itself is so very amazing, so very extraordinary, so very magnificent. And for this to generate in the present sense, okay, you'll see that nature had to put things in the perfect balance. You'll see that the amount of land, the amount of water, the amount of air, the amount of salts in water, the minerals on the land, the type of gases in the atmosphere. It's if you go to think of it, and there are n number of things which the nature went into balance. And it's only after that, okay, And in spite, you'll see that it's not immediately that okay, nature put all these things together. Okay, it took time to evolve. You'll see that from a molten surface to a hardened surface, then you have water coming in, then you have the gaseous envelope. We still did not have the ozone layer then. Okay, and in fact, that reminds me that I did ask you all about did land have life earlier, or did water have life earlier? And one of you all did put up that it was land, it was water. But as I said again, scientists are divided upon it. Now, why is it that it is so believed that life should have been in water first? Is because we did not have the ozone layer, and without the ozone layer, the ultraviolet rays of the sun were free to come all the way to the surface. These are very high intensity rays, and that's why life was very difficult on land. It's only when gradually the ozone layer develops. So you'll see that how gradually nature was putting one thing, second thing, third thing, fourth thing, and n number of thousands and millions of things together, and all these formed ecosystems the right distance from the sun. You'll see that if you see the planets like Mercury and Venus, very, very hot. If you see Mars, you have a lot of carbon dioxide. You'll see that as far as Saturn and Jupiter are concerned, it's a lot of gaseous mass. And of course, out of question as far as Uranus, Neptune, they're very, very far. So the perfect distance that the Earth has from the sun, that's 150 million kilometers at an average. All of this, the tilt and the gravitation and all these eventually set a perfect blend for life to come upon this particular planet. In spite of all this particular blend, it took a few billion years for life to come upon our planet as such. So it's so very interesting, and we should consider ourselves so very lucky that we have evolved as living beings on a planet which as of today probably is the only planet which is sustaining life, and which is an active planet in itself. Okay, it's an active planet in itself. So you'll see that you look at the moon, it is dead. You'll see that you look at Venus, it's sort of dead. Okay, you'll see that this bubbling thing, the natural aspects that have come on the Earth's surface, simply are wonderful. By the way, I have a question here, or rather a point. I don't know. See, Ami says that, sir, I heard that the Earth was first very hot and then very cold. That is, it faced ice age. So when did the ice ages happen in respect to time? I would have been very, very happy to show you all the documentary that I was speaking about. It speaks all in details about all these things, and particularly when I blend this with certain explanations with regards our syllabus, it makes it more interesting. Yes, the Earth was initially very hot, but when we speak about the coldness, there was a certain phase. Yes, there has been, and in fact, it's not one phase. There have been cycles. In fact, climate change. If you very broadly try to understand what climate change is, it is nothing but the swing of the temperatures on the surface of the Earth from being very, very hot to being very, very cold as such. And the Milankovitch cycles help for the Earth to switch here and there. And of course, then you have planetary aspects. Say, for example, say the present arrangement of continents is such that it's in between these continents that you have oceans, and it's in the center of the ocean that you have the volcanic eruptions which are taking place. And though volcanoes are so to be harmful as far as human life is concerned, remember that the energy, the temperatures that are maintained on the surface are with the help of these volcanoes. And that is why it is believed that when you had all these continents together, that Alfred Wegener speaks about his Pangea. But let me tell you that as far as this unified continent, one continent is concerned, this is not the only time that we have had all the continents together and forming one large mass continent as such. It is believed that before we had the Pangea, you had before that we had these occurrences where we called them as these land masses were called as Rhodania. Okay, you have Rhodania 1, Rhodania 2. So possibly Pangea is the third time that all the continents came together. And it is believed that this cycle is of 1 billion years. Now, again, this is a geometric calculation, let me tell you. And it is again believed that, say, we are 4.6 billion years down the line, and say another few hundred million years, all these continents may again come together. That's very interesting to note. And we see that all these continents are on a continuous move, and that is why we call the Earth as an unstable planet. In the geographical sense, as far as the life sense is concerned, all life is sustained because of all these combinations that keep on happening around us. So it's so much to study, so much to understand as far as the whole Earth is concerned. Now, I think I have covered majority of the things as far as uh, the geological time scale is concerned. The life part of it, the last 600 million years, are divided into three forms of life: the old form of life, the new medial form of life, and the new form of life. Old form Paleozoic, mid form Mesozoic, new form Cenozoic, which is spelled CENO or CAINO. You'll see that you find different spellings. Now you'll see that these eras are divided into periods, and it is on these periods that we spoke about the mnemonic that we have formed, that camels often send to us, tend to sit down carefully and all that. Okay, so it gives you a link into all those periods that may have happened in between. Okay, so that is all that we need to know basically on a very superficial scale as far as the so to say the geological time scale is concerned. Then you'll see that as far as the first topic in your syllabus is concerned, we have covered a significant amount of that. You'll see that we have classified the whole Earth into systems, and of course the branches of geography and the branches of physical geography. All this was done. Say, I did not tell you that we were doing that, but in the process that we were understanding all these things, we went through a significant amount of our first chapter as such. And coming to that, we were speaking about the Earth systems, and it is these Earth systems, the land system, the water system, the air system, and of course on these dependent the biosphere system. And then you have the new entrant into this, the very cold temperatures, the ecosystems, and the ecosystems of very cold temperatures, and that sphere is called as the cryosphere. So we have done that aspect also. Okay, and the last topic there is contemporary issues in geography. Now, what basically do these contemporary issues mean to us? You'll see that off late, okay, you'll see that we divide this into the geographical information sciences, climate, environment, and society, humans in the globalizing world as such. Okay, you'll see that as far as this aspect is concerned, we see that man has grown to a significant number, and he is been dominating this planet. At least he says so. He has been dominating, and the numbers have grown significantly high. He has adapted himself. So a contemporary issue in geography would be how man is pacing himself. Then you'll see that another contemporary issue is that the climates are changing, and these are having impacts on the environment around us. And of course, as far as both these aspects, the human and the physical aspect is concerned, all these nowadays are mapped with what is called as the GIS, the Geographical Information System, is nothing but digital mapping systems, so to say. Okay, I'll try to fit up all these things. Okay, we'll do these things first. Yeah, introduction to GIS, applications of GIS, visualizing geographic data in 3 dimension, geographical data analysis, web GIS. All this is our contemporary issues in geography. Then you'll see that GIS modeling in environmental change, new digital worlds. Okay, field methods, remote sensing, and marine geography, GIS, and geosciences. All these form technological kind of contemporary issues in geography. And then you have medical healthcare in geography. Of course, we should be taking this with this aspect here. Just put it this way. Okay, so you'll see that medical and healthcare geography, which is in fact the thing which is happening around us in this special pandemic of Corona or COVID-19 that we have around us. Geographical analysis of transportation, how resources move from one region to the other, and then we'll see that how from a rural society we have moved to a city in the Western tradition, world regional geography, globalization, economic geography, human geography, urban geography. Okay, Of course, it should not be the American landscape. In fact, this is a picture taken from the Google, so it states that. But you'll see that it's all landscape. Any landscape in any part of the world could be taken up. Geographical analysis of urban social issues, contemporary Europe, I would say, geography, the urban part of it, and race and sex and space and place. All these are so very interesting things to be learned as such. And then something between the physical and the human part, the natural disasters that we have, the climate change, the current geographical issues, introduction of sustainable cities, because we know that man is a major polluter nowadays. Okay, then the global change. What are we doing at a local level? What are local actions which are taking place? Are we evaluating the environment around us, and so on and so forth? Then environmental planning and management, and of course human modifications and of the natural events as such. Okay, and then of course climate, weather, physical geography, national park landscapes, fluvial geomorphology, environmental restoration, climate and weather, and advanced physical geography. All this is nothing but what can be identified as contemporary issues in geography. So much to be done in geography, and mind you, I keep on telling you all that don't say blend yourself into a specialist. I'm a GIS specialist, I'm a climate specialist, I'm a geomorphology specialist. You'll see that every contemporary issue in geography requires you to be informed about everything around you. Okay, and that's why this subject is called as jack of all trades. Okay, you need to know everything to some level at least. Okay, to understand the whole, to get the whole essence of geography as a subject. It could be geography in the faculty of science, or it could be geography in the faculty of commerce, or it could be geography in the faculty of our own faculty, that's the arts faculty as such. So that is the last topic as far as the first chapter or the first unit that we need to know. And the second unit is the first of the earth system, that is land. Okay, and as far as land is concerned, we call it geographically as the lithosphere. Now, though man lives on the surface, you'll see that man is a very inquisitive animal, and you'll see that he wanted to see what is in the sky, he wanted to see what is in the water, he wanted to see what is in the below the land surfaces, and so on and so forth. So researches are constantly taking place. And thus, when we start with land, okay, our first question would be, since we have done geological time scale and what has been happening through this geological time scale, we know that the surface is made up of land. Okay, but what happens beneath the surfaces and etc. So before we speak about land, land was formed from something which came from interior. So obviously the question would be that shouldn't we be learning what happens in the interior of the earth first? Yes, we should be learning what is happening in the interior of the earth. And that is why we start with the lithospheric studies. Always, you'll see that you look into any book, a reference book, a textbook, you'll see that when you start off land, we initially start with nothing but interior of the earth. And thus, we should be, okay, but before we go into the interior of the earth, shouldn't we be seeing into say, get to the scale of it? What exactly does this mean to us when I'm speaking about the interior? Before I go to the interior, I should be looking into what is happening up and above and below. Okay, so as far as you'll see that the tallest building, the world's tallest structure, the Burj Khalifa is concerned, you'll see that this white thing here, okay, this is the Burj Al Khalifa. And then you'll see that you come to the Matterhorn peak, which is the tallest peak in Europe. Okay, and then as compared, you'll see that Burj Al Khalifa is dwarfed because it's less than say it's around 2,500 feet only, while the Matterhorn is 15,000 feet, and all the way you go up to the Mount Everest, you'll see that it's 29,000 feet, and you'll see that it just leaves around how much? Say around a couple of thousand feet. It could very well be that if I'm standing on the Mount Everest and I see a normal commercial airliner flying by, you'll see that it could look to be very near to me, though I would be say the plane would be flying very high, that's 35,000 feet, but because I would be at 29,000 feet, it's only 6,000 feet that would be separating myself and from the height of that particular. So if you see here, okay, you'll see that the Burj Al Khalifa is here, and Mount Everest is here. So height wise, it's very interesting. Then as far as depth is concerned, let us see what is happening with the depth. You'll see that the Challenger Deep, the Mariana Trench, is this particular deep. Okay, you'll see that these are the different um, feats that have happened. You'll see that as a whale. Okay, you'll see that normally a whale can dive down to a distance of around average around 3,000 feet below the mean sea level. Then you have the Titanic, which sunk in the last century, and it has all the way down to 12,000 feet. And then you'll see that snail fish, okay, are found 25,000 feet below. And you'll see that an unmanned submarine, the maximum that man has ability to send it down is 35,000 feet. So 35,000 feet here and 35,000 feet here. Okay, so a total variation of 70,000 feet as such. Okay, then in another concept or context, let us see all these things happening. Okay, you'll see the deepest places on the earth, a scale representation of the deepest places. I've taken this from Google. They're all there on this, and I hope you can see these letters here: A, B, C, D, E, F, G, H, I, J, K, L, and down you are going to have M. Okay, now we'll just visit to each of these and come back to see what these are. Okay, now A is the deepest canyon. It's Kota Hausi. It's a canyon in Peru. Peru is a country in Southern America. Okay. However, it is believed that the deepest of the canyon of late has been identified um, near where the Brahmaputra actually enters India. Okay, if you can imagine your studies of regional India and the Brahmaputra entering, you see that the Brahmaputra curves. It takes a C-shaped and then it comes into India. It is believed that somewhere there there is a very deep canyon. Of course, there are difficulties and debates about the actual depth of that particular canyon. But given this diagram in front of us, you'll see that 11,000 feet, 11,000 and a half feet deep is the canyon. Then, as far as the B section is concerned, you'll see that there is this cave, this deepest cave by the name Kurbera Cave. Okay, Kurbera Cave. It's somewhere in Central Asia, I believe. I'm not very sure about this. I'll have to check this. And in fact, this could be an assignment for you all, that to find first that if the deepest cave is correct. Secondly, deepest canyon is correct. Secondly, where is this particular Krubera cave? As such, the deepest of the cave, it goes all the way down 7,000 feet. Then you'll see that Lake Baikal is the largest freshwater lake on this planet. Okay, this is supposed to be 5,000 feet deep. Okay, this is in Russia. You can see this. You can locate this on a map. Okay, then the deepest mine, you'll see that how man has gone deeper, and these are called as shafts. You'll see that man goes crisscross as far as identifying minerals and extracting them is concerned. The deepest mine, obviously the mineral has to be that worth, and obviously this has to be the gold mine. Okay, so 12,000, I would say nearly 13,000 feet, the Tautona gold mine. This is in South Africa. You can locate where it is again on the world map. Another interesting thing. Then the deepest open mine. Now this is a closed mine, let me tell you. Okay, if you remember this movie Kala Patthar, most of you all were not born at that particular point of time, but it is screened on Sony. Okay, the it's based on Dhanbad, a coal mine in Dhanbad. Okay, you'll see that you go down, and then of course you go sideways and you just extract the minerals and then you send it up. Okay, these are called as deep mining, and this is open cast. Okay, if you have minerals at the surface, you just pull it out. So E is the deepest open mine. This is in the Bingham Canyon mine. That's in United States. Again, which part of United States is this? Is an activity for y'all. Then we have the deepest foundation. Okay, you'll see that Deepest foundation in the sense that if you have seen, when a new building comes into construction, you have to go deep, and it has to hold the surface, right, so that it does not collapse. Otherwise, if you had built the building just on the surface, it could have easily toppled itself in an extreme climate, say winds or heavy rains. It could have floated away. So that the building catches to the surface, you have to have what are called as foundations. Now, the deepest foundations are for the Petronas Towers in Malaysia. Remember that before the Burj Al Khalifa, uh, sorry. F is first the deepest railway tunnel. Okay, this is not much deep, but then it's the deepest. You'll see that the Sikon tunnel in Japan, F here, F. Okay, this. Okay, Sikon tunnel in Japan is 790 feet. Then the G thing, these twin towers, the Petronas towers as they are called, the foundations have been as deep as 394 feet. So if we transfer this into meters, this comes nearly something about 100 meters. So they dug holes into the surface 100 meters deep, and then the foundations were laid, and then slowly the Petronas towers came up on that. Okay, so that is as far as the G part is concerned. As far as the H, we all have just seen in the earlier one that the tallest building of this on this planet presently is the Burj Al Khalifa. It's in Dubai, 2723 feet. Again, this is nearly 100 meters tall. Then then we come to this IJK. You'll see that these lines are going down. So I'm going to take you down as well. Okay, and then you have this L here, HIJK, and then we will have this M, but we'll go there one by one. Okay, probably this is something again that we have discussed in the earlier picture, but let us see what L, J, and K are. Okay, you'll see that as far as L is concerned, okay, it is the deepest man-made point, 40,000 feet. Okay, it's the Sakhalin. It's an oil well in Russia. Sakhalin Islands, you can see where they are towards the eastern part of Russia. Near that, you're going to have an oil well, and the Russians are digging out well from as deep as 40,000 feet. 40,000 feet again is going to be more than 1 kilometer deep. Okay, 1.5 kilometer, if I'm not wrong, somewhere around 1.5 kilometer deep. Okay, then you'll see that deep water horizon. Okay, this is HIJK. Okay, now what is that? Okay, you'll see this part. Okay, this deep water horizon, possibly the fresh water available down there, uh, is K, and then of course J is the deepest scientific exploration that went to the distance of 40,230 feet. Scientific exploration in the sense people may have actually gone in there. By the way, you'll see that Russians, the oil well is also that deep, and you'll see that exploration also was as deep as 40,000. Probably they were carrying their own oxygen mask, otherwise it would have been difficult for them. And then the deep water horizon is 35,000 feet, the deepest level to which you can find water possibly. And this deep water is also called as fossil water. Now you can read about what fossil water is, because it's a very interesting, important, environmentally sensitive issue which is happening uh, as far as um, agriculture which is practiced in Saudi Arabia is concerned. You can go into the details of that. If you are not able to find that, we'll go into that at some other point, say probably the next lecture. So that is as far as deep water horizon. Then you have HIJKL. This is L, the depth of a sperm whale. We said that 4,000 feet is the distance to which a sperm whale can go down. And then we have the M point here. This is the M point. Deepest point underwater, Mariana Trench, which is as deep as 35,000 feet, 35,800 feet. It's 36,000 feet, we could say. And you divide it by 3, that comes to the number of meters. So say 12,000 meters, that's going to be 12 kilometers deep, 12 and a half days. Then this is deepest solo dive. Okay, 35,000 feet again. This is the solo dive. This was done by James Cameron. If you can remember who James Cameron is, Uh, this name, I think you should be knowing this. Let me know if you can remember this. Then we come to LMN. This is finished here, and now we go to the interior of the Earth, and then we come to LMNO, peak of Rocky Mountains. Of course, I don't know where they have placed this, but the peak of Rocky Mountains is because this is probably a diagram from the United States. The Rocky Mountains, I would have placed the peak of yeah, they have written peak of Mount Everest here. Oh, then P, the Mohoric discontinuity. That's the shift that happens from the crust to the next second layer. Okay, and this is say how much? 1 lakh feet down, 1 lakh feet. So that's somewhere around 30 kilometers from the surface, you could say. And then you have the Gutenberg discontinuity. This is here. That's between the second layer and the third layer of the Earth. That's the mantle and the outer core. It is as deep as what? 9 million feet. 9 million feet would be 3 million meters, I would say. And 3 million meters, if I take out three zeros from that, what could be around 3,000 kilometers. Yes, you'll see that the depth of the mantle is around 2,900 kilometers. So that matches with our calculation, interestingly. And then down here, that's between the outer core, which is a liquid. You must have studied this in earlier studies. And then you have the inner core, which is solid. Okay, and at their boundaries, you have the layman's discontinuity, and this is at 16 million feet. 16 million feet would again be around 5 million meters. That would be somewhere around 5,000 kilometers. Okay, yes, the center of the Earth is somewhere around 6,400 kilometers. So that falls into logic to quite an extent. This is say the most interesting part, and of course we are going to look into one more diagram, which will again help us to understand how deep the center of the Earth is from where we are presently placed. Okay. This is the whole thing in a continuous sequence, and let us go into the deeps. What I've done is I found this on the net, and I have split it into two diagrams, and then I've just expanded it because reading through them was a difficult task then. So what I've done here is the highest and the lowest points on the Earth. Okay, you'll see commercial airplanes. We already said 29,000 feet Mount Everest. Okay, then so you'll see that this is an interesting biological fact. 26,000 feet is where oxygen levels are insufficient to sustain human life, and that is why you'll see that mountaineers climbing to Mount Everest for the last 3,000 feet, or in fact, much before that, they carry their own oxygen cylinders. And that is why somebody traveling to the or scaling to Mount Everest without oxygen is some feat, I would rather say. It needs to be a very healthy person with very strong lungs to travel to that particular height, walk to that particular height, because you'll see that at that height, even walking a few meters consumes a lot and lot of oxygen, which already is very less around us. So that is 26,000 feet. You can keep this information in mind. And then we have this highest active volcano, okay, Ojas del Saldo. Again, a task for you all. Where is this? Okay. Then we have the higher clouds, the cirrus clouds as they are called. They are at around 18,000 feet, or let us say 6 kilometers. Okay. And then you'll see that skydiving, okay, when people dive out of for skydiving, the average height is around 12,000 feet. Then Mount Fujiyama in Japan is 12,000 feet. And then you come down here, you have Ben Nevis. Ben Nevis is the tallest mountain in Alaska, if I'm not wrong. Then these are the tall buildings, the Burj Al Khalifa. Let's see if I've put it here. Yeah, the Burj Al Khalifa. And then next to it is the Shanghai Towers. Okay, this white object here is Shanghai Towers. And of course, the Shard, Europe's tallest building. The Shard is you can search for the diagrams or pictures of these. Shanghai Tower, or on Google. Okay, and you can post this in our group as well. Okay, then now we start going deeper. Okay, 3,000 feet. You'll see that Bingham Canyon, we spoke about that in the earlier picture also. You come down here, depth of the Grand Canyon, okay, is here, okay, 6,000 feet. You go down, Wales can go deepest to 10,000 feet. Earlier one said 9,000 feet. Then we come to Titanic. Okay, the Titanic rests very low. Okay, that should remind you of a question that I have already asked you, 12,500 feet. You go deeper and deeper and deeper, you'll see that snailfish can go deep as 26,000 feet. Then it's 30,000 feet. That's the deepest of the borehole that man has dug as of now. And then you have this, that's deep water horizon, deepest water well, deepest oil well, sorry. And then deepest solo submarine is to around 3,500, let us say, not 3,500, sorry, 36,000 feet. And then the depth of the Mariana Trench, and then of course the Sakhalin project I spoke about it, and then the Koala borehole, deepest artificial point on the surface of this particular planet. But let me tell you that all this is nothing when I compare it to these depths here. Okay, these are just in feet here. These A, B, C, D, E, F, G, all the way up till N, or let us say O, P, O. Okay, but you'll see that as far as PQR is concerned, PQR, these are kilometers deep, kilometers, several kilometers, hundreds, several hundreds of kilometers. In fact, I said that the center of the Earth is nearly 6,500 kilometers from where we are sitting right now, a bit more than that. Okay, so that is as far as the uh, deeper levels are concerned. Of course, we have still not started. We partially started, I could say, but we have still not started in the geographical levels, the geographical aspect as far as the interior of the Earth is concerned. Okay, let us do that now. Okay, you'll see that if you look at the structure of the Earth, okay, you'll see that it looks something like this. The right one first, okay, you'll see that you have these cylindrical spherical balls, you would say. The outer one is very thin, and it's called as the crust. And below the crust, you have the mantle, and below the mantle, you have the outer core, and below the outer core, you have the inner core. An obvious question would be, why is it that to others, while the crust and the mantle, though the crust is further divided into two parts, the mantle, in fact, nowadays is divided into four parts? Why is it that the core is referred to separately and the others are not? Because of the state of matter that they are in. The outer core is in a liquid format and the inner core is in a solid format. And in fact, it's the arrangement between the outer liquid and the inner solid that has led to the formation of gravity and magnetic field, all this, which are unique features as far as the Earth is concerned. As I said, I keep reminding you of the best of the conditions for life to evolve. As far as the left one is concerned, I'm just going to introduce this and we'll stop here for today and we'll meet next week then. You'll see that we spoke about this being 6,371 kilometers, the center of the Earth. As I said, approximately 6,500 kilometers is deep is the point of the center of the Earth that we are sitting from. Now, before I leave, I've posed you a lot of questions and a lot of activity that you could do over the weekend, and I'll leave you with one more question. This is a very commonly asked question, I would say, in competitive exams, or it could be in these quiz competitions and so on and so forth. That if I dig a hole from one part of the crust to the other part, say I'm sitting in India and I start digging and I come out on the other side in the US. Okay, I would not exactly come out at the US. I would actually come out, if I have to dig through the center of the Earth, I would come up somewhere in southern hemisphere, probably South America somewhere. And then if I drop a ball from one side of the hole, okay, what would be the position of the ball? Okay, it will drop down and it will fall off from the second, the other side of the Earth, or it will keep on moving, or it will stabilize somewhere. What could be the possible state that this ball could be in? Of course, this is a hypothetical condition, but applying physics, what should this be? I will leave you this particular question and I'll stop my share here, and I will then just check if you have posed any questions for me. Uh, Surprisingly, the number of students today is significantly less. I don't know why, but yeah, if you have any questions or if you already have answers to the questions I have posed you all in during the lecture, you could just post them here, and let us see if we can take some of them here. Okay, we've already crossed 50 minutes, but just a couple of minutes. If you have questions, we could surely um address a few of the questions. Okay, and if you don't have any questions, then of course we could stop here, and you could move on to your next lecture. I'll meet for a couple of seconds, just in case you have answers, questions or answers anyway. Otherwise I would be uh, ending my broadcast. If you have no questions, then I would stop my broadcast here. And as I always say, stay home, stay safe for the weekend. Have a great weekend. Thank you very much.